Alrighty. Hello, Year 12. So, this is going to be your last lesson on projectile motion. Next week, we are moving on to forces and momentum. This is all stuff you should know already, so it's less of me teaching you stuff and more of like reviewing stuff, which you've been doing basically for the past 2 weeks. But this is the last time we're going to visit this until it's time for your test. Alright, so I'm going to start off down here. These, equations. You should all know how to use these, you should all know how to rearrange these. Okay. Next, we have not velocity, we have motion in two directions. So we have two vectors. You have cos theta for your horizontal and sine theta for your vertical. Okay, just a couple of tips. Time of flight is determined by the vertical component of motion. Initial and final velocity may be resolved in vertical and horizontal components. Final velocity can be determined using the vertical and horizontal components and trigonometry to determine the direction. Vector addition and subtraction may be used to determine vector quantities. Also, do not forget, when you are working in 2 dimensions, you must have the angle. This angle is required in 2 dimensions. Okay? It's not just 1 dimension, not just going, it's going up. Not going across, it's not going straight up, it's making an arch. Okay, because it is a parabola. Alright, so vector addition and subtraction. You have two vectors, A and B. When you add them together, A and B, you get a line going through the middle of them. That's A plus B. Okay? Next, when you have A and B, you do A take B, you have the line going outside of the two together. And you have a negative B going down here as well. Okay? So, acceleration of an object undergoing projectile motion is due to gravitational force due to the gravitational force it experiences. So when you are writing out the components that you have, the velocity, time, displacement, whatever, when you're writing out whatever your values are, always make sure you write acceleration. Okay? Because that is always going to be in your projectile motions. Acceleration, constant, going down. And also we are assuming all projectile motions are happening on Earth, which is why it is 9.8. Okay? These will change, this will not. Acceleration, according to Earth's gravity, will always be 9.8. Or 9.81 if you want to be pedantic. Okay? So, in the absence of air resistance, projectile motion is parabolic, which means it's a nice even curve. Okay? So, velocity varies to the motion and is always tangent to the curve. Okay? Tangent, tangent, tangent. Okay? Acceleration is always constant and directed down. Don't want to see your drawings of the acceleration going up. Acceleration goes downwards because gravity. Okay? Absence of air resistance, only force acting on the object is gravitational force. No force acting in the horizontal direction. Therefore, horizontal component of the velocity remains constant. When you're doing your D&Ds and you're drawing your expected arc of things, if you're doing projectile motion, well, this specifically launching something, first of all, this should be down in gravity and these should be at tangents. And second of all, your horizontal lines should all be the same length, because they should all technically be the same. In theory, they're all the same, because we are neglecting air resistance. Okay, and what should change is your vertical values. Okay, because here we are going up and getting slower, blah, 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 blah. We're hitting 0 at the apex, right at the peak, it's 0, and then when it comes back down, it goes negative. Okay, and forget, velocity vector has direction, not just magnitude. Direction. Negative tells us it's coming back down. No negative sign, it's gonna go up. If you're calculating all the way through and you're drawing your graph or your theoretical graphs, and you get to here it's 0, and then you start going down, and you do not put that negative sign. I'm just going to assume instead of having a parabola like this, somehow you manage to throw a ball and it's gone like this. Okay? This is a no-no. You want this. This is good. Remember, negative sign, no negative sign. Negative sign needs to come back down. Okay? Horizontal component of velocity remains constant. Vertical component changes through motion. Total velocity at any point is calculated using vertical and horizontal components of velocity. So looking at the speed of an object is the magnitude of the velocity. So basically we're looking at the average speed. Okay? That is calculated using Pythagoras' theorem. Okay? We've got the horizontal velocity. We have the vertical velocity. We're trying to find this here, which is the speed. You do Pythagoras. Okay? E squared equals the horizontal component plus the vertical component on the velocity. You do that, you get your answer. Ta-da! Math. Okay? Alright. And next, direction is found using tan. Yes, I understand this is annoying, and yes, you do need to remember to do this because, once again, we are launching something. It is in two dimensions. That means it's not just going straight, it's at an angle. It's going somewhere else. In that case, you need to find what the angle is. We always use tan to find angles. Very rarely are we going to use sine or cos because sine and cos give us your vertical and your horizontal components. Therefore, we use tan to find the angle. Okay? So, total velocity of 8.6 meters per second at an angle of 54.5 degrees above the horizontal is what is happening here. This lovely diagram. Okay? Alright, in the absence of air resistance, projectile motion is symmetrical if the launch height is at the same height as the landing height, sometimes called unilevel motion. Okay, so in unilevel motion, this angle and this angle are the same. Okay, similarly, two angles, theta and phi, will give the same range if theta plus phi equals 90. Okay. So if you have one thing being projected, and then you have a second thing going above, and say one angle is 50 degrees and the other one is 40 degrees, they will end up giving you the same range of motion. So as a diagram, we draw that. We have one here and then one here. Say this is 40, this is 50 degrees. Okay. Well, my terrible diagram because I can't draw. But so here we have a diagram of theta is 40. Down here, sorry, yeah, theta is 40, and over here we have phi as 50 because these two angles add up to 90 degrees. They're going, if you throw them from the same start point, they're going to end up at the same end point, despite the fact that you're going to get two different heights. Okay, you may get two different heights, but they will end at the same spot because the angles add up to 90. So they have the same range. Okay, different heights, same range. Okay, as shown in this diagram here. I find another drawing one. Anyway, so we have a 10-degree angle down here. As you can see, not much height, but same range, a good range. We have an 80-degree angle up here, lots of height, same range. 80 plus 10 is 90 degrees. Therefore, these two, doesn't matter that one has a hell of a lot more height, they're going to have the same range. Okay? And as you're well aware, maximum range of a projectile motion determined by optimizing both vertical and horizontal components. Maximum range comes at a 45-degree angle. Okay? So this is the formula for vertical displacement. Okay. In this situation, projectile has initial speed v, then displacement is 0, v naught is sine theta, and a acceleration is gravity. Okay, so we have this formula, we arrange it to get t. Okay, the range, so this is a proof, before I continue, this is a proof for determining the best angle. So if you ask the question like, prove that 45 degrees is the best angle to launch things at, it won't be worded like that, but that's basically what the question is asking. Okay, and you have the range, and the range of a projectile is given by this. So you know that VH is cos theta. You have your D equals V cos theta. So D is range. D is range. D is V cos theta because you're subbing in this for VH, and then you're subbing in T in this formula with this from up here. You get this, which is starting to look a lot like specialist trig proof. Okay, so range is equal to negative 2v squared cos theta sine theta over g. Okay, so the maximum value of range requires to find the maximum value of cos theta and sine theta. This occurs when theta equals 45. Okay, you should be able to do this. Proof, it has been asked in exams before. It may be asked in year 1. This is something you need to know how to do. Okay, so maximum range of a projectile is also affected by your launch height. Clearly, if you're launching something from up here and it is going and landing on a different level, it's going to go further because we have launch up, it goes. If it were to be if it was going to be on the same level, it would finish here. But it is falling to something below it. So it keeps going. It has additional time to move. Therefore, it is going to land slightly further away. Time taken, yeah, uni-level projectile motion. Then, okay? So, launching something from a higher position and letting it drop down to someplace below is going to give it a greater range. Okay, so initial speed of a projectile from the analysis above, this and this. Okay, time for flight for a uni-level projectile motion is given by this. So time is equal to 2v sine theta over g. Therefore, time is inversely related to speed. So therefore, as the speed increases, so does the time of flight and the maximum range. Okay, so the faster it goes, the longer it goes, and the further it goes. Okay, 90. Next, we're looking at drag forces. So in most situations, air resistance is assumed to be negligible. Drag forces are the exception to that rule. Okay, so an object with a medium experiences drag force. That's given as FD, so force, and then down the bottom is drag. Force is affected by number of interactions, blah, 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 blah. This is all something you can do without me having to read it out to you. So, but I will highlight 3 factors to be aware of. 1, surface area. 2, speed. And 3, the density of a medium. Okay, density of a medium is kind of like the texture of it and not like how thick the thing is as well. Okay? I'm not going to read that out for you. You'll have eyes. And this is going to be uploaded to the app as well. So drag coefficient is a capital C. Make sure when you write the equation, you write a capital C. If you write a lowercase c, you have now put it at the speed of light. Okay? We're not up to that. We're not doing waves and particles into term 3. So, capital C for drag coefficient. Okay? Blah, blah, blah. Factors are given and in this expression here. This should be on your formula sheet. So drag force is equal to 1/2 rho a capital C V squared. Okay. Next we have terminal velocity. Velocity of a freely floating object from the net force acting on the object is 0. So force is 0, therefore acceleration is 0. Okay. Drag force formula your weight formula. So weight is mass times gravity, or force is equal to mass times acceleration. Same thing. Okay, so sum of the forces equals 0, which goes to 1 over 2 rho a c v squared, which is the same as mass times gravity. Okay. So drag forces affect both the vertical and horizontal components of the velocity. So drag force always acts in the direction opposite to the direction of motion. So if something's going down, the drag force is going to push against it and go up. If something moving to the left, it's going to push to the right. Okay? So, like in the examples here, we have the velocity is going this way, the drag force is heading in the opposite direction. Okay? As the projectile moves upwards, it experiences a greater net force acting downwards. The horizontal component of the drag force results in an acceleration in the horizontal direction, and VH is gradually reduced. The range decreases. So when you have drag force, something will not go as far as it should because it has a force acting against it. Okay, so these two combined together results in a greater vertical acceleration and reduces the time of flight. This reduces the maximum height the object reaches. Okay, so if something normally, when you throw it, goes to about here, when you throw it and you put drag into play, you might get to a height of about here. Okay. Combination of both of these factors result in a reduced range, and a lower maximum height. So no drag force, you get a nice even parabolic arc. Boom. Okay, with drag force, it's uneven and it's not nearly as nice, and you do not get nearly as far nor as high as you could have without drag being present. Okay, that's it. That is the entirety of what you need to know for projectile motion. Continue with the questions. You should all have your books by the end of this week. I'm really hoping you guys go and get them tomorrow or some point, preferably before the end of this week. I will take photos of the rest of this chapter and have them available for you, or we can go through them together in class. But yes, that is it. Alright, see you tomorrow.